Chapter. I think we are okay for now. Okay, so it's a real pleasure to introduce Doug Durian. Doug is a professor of physics at the University of Pennsylvania, and the title of his talk is The Statistical Mechanics of Granular Clogging. Just a brief bio to introduce Doug. Doug Durian obtained his A.B. degree in physics from the University of Chicago in 1984, and his PhD degree in physics from Cornell in 1989. After a postdoctoral fellowship at Exxon Research and Engineering, he joined the physics department at the University of California, Los Angeles in 1991. In 2004, he became professor of physics and astronomy at the University of Pennsylvania. He was appointed Sigma Xi Distinguished Lecturer for 2003 to 5. He was named Fellow of the American Physical Society in 2005 and served as a member at large of the APS Topical Group on Statistical and Nonlinear Physics for the term 2005 to 8. Currently, he's past chair of the APS Division of Soft Matter, DSOFT. With Andrea Liu, he recently co-founded the Penn Center for Soft and Living Matter and serves as the associate director there. Durian's research interests are primarily experimental, with a focus on the microscopic origin of behavior in particulate and particle fluid systems such as granular media, foams, and colloids. In these areas, he has contributed a number of new techniques, analysis methods, and theoretical concepts. He actively collaborates with theorists as well as experimentalists from many disciplines outside physics. So thank you, Doug, and without wasting any further time, I'll let you get rolling.
All right, thank you so much. And thank you for the invitation and wonderful opportunity to speak today. And I should say congratulations and my apologies for intruding upon your anniversary.
Thank you so much.
So today I'd like to talk to you about the video we see here on the left. It's a granular hopper. These are actually tapioca beads, and it's being played in a little bit slower than real time. And you can see that it discharges the grains for some while, and then it clogs sort of unexpectedly. So to me, this raises two questions, which I'm going to try to address, at least begin to address today. Is there a clogging transition, and what is the nature of the clogging transition if you make the hole size larger? If you make it large enough, you know well that the grains will just entirely empty out of the hopper, as in a common hourglass. But if you make the hole small enough, or if you design your little egg timer poorly, it'll clog. So is there a clogging transition, and what is its nature? Next, we'll get a little bit microscopic and think about what's going on in the flow states that actually causes a clog to form, as opposed to asking what is the stability of an arch once it has formed. All right, so let me begin just by setting the stage with a little bit of context for where my interest in this whole general topic comes from. All right, if I can change slides. There we go. So for me, the big picture is it's physics beyond jamming. And we now know lots and lots about the jamming phase diagram and how it looks for many disparate systems and how it's very common amongst them. We know how there's a special point called J, and the proximity of your system to point J controls behavior and in a very important and interesting and subtle ways. We know lots about this, all right? What's key is that for this to be a useful construct, and it is useful, your system has to be basically at one point in this system. You need to have a uniform system, right? So all the state variables have to be the same throughout the whole volume of the sample. And for actually a lot of granular situations, basically getting a granular system into or out of a jam state, that's not true. There are gradients in state variables. You know, the flow is fast here and slow there. Boundaries are important, like in clogging, that's clear. The boundary plays just an absolutely crucial role. And also, there can be history, dependence, and non-local effects. All right, so in fact, clogging contains a lot of physics that's distinct from and on top of jamming. So even though in everyday life we may say, well, you know, my hourglass jammed, in a sort of a technical sense, clogging and jamming are distinct. And there's additional physics in clogging that's not recognized in the structure and behavior of the jamming phase diagram itself. So that's part of my interest in this topic. Why granular? So of all these different kinds of materials, grains, bubbles, colloids, fuzzy molecules, etc., why grains? Well, lots of reasons. So basically, grains are everywhere. We're not very good at handling them. Bad things happen, right? They clog, they demix, there's explosions, there's collapsing silos, we waste lots and lots of energy. I won't go into any of this, just to say that, you know, grains are everywhere and we don't do a very good job handling them. And the reason why is not difficult to see. They're disordered. The grains are arrayed. If you look at a snapshot, it's very, very amorphous. Grains are nonlinear. The mechanics are very nonlinear. Tipping a bucket to a few degrees results in no flow, but if you tip it farther, it flows. So there's thresholds. So just the act of flow itself is nonlinear. It's very dissipative and frictional, and friction is always a headache. It's far from equilibrium. Relevant energies are huge compared to KT, and of course, it's a many-body system. So really, for all these reasons, grains are unpredictable, they're very hard to engineer, and they're very hard to understand. So of all the topics, why clogging? Well, as I said, clogging is hard to understand, and it is, in spite of the picture, quite important to understand. For me, personally, it's also, I find it interesting, additionally interesting because it's familiar from everyday life. That's personal taste. And actually, since I come from Pennsylvania, it's almost a statutory obligation to study clogging and think something about arches and their stabilities. All right, so to begin with the content proper, here let me discuss two iconic features that you can see in an hourglass. One answers the question of why we make hourglasses with sand, and the answer, rather than water, and the answer is because the discharge rate is constant. If you count the number of grains, or if you measure the mass per unit time that comes out the hole, you'll find it's constant. It doesn't depend on the filling height, by contrast to the fluid. It doesn't depend on the pressure head, by contrast to the fluid. And interestingly, it also does not depend on the grain size. We will take advantage of this, and I'll explain a little bit more about this in the next slide. So that's one iconic feature. The other iconic feature, of course, that doesn't happen for fluids that we're all about today is it clogs. And the phenomenology in general, if you have grains that are fairly monodisperse, then roughly, and if they're not really oblong, right, if they're sort of compact, then roughly you can see clogging pretty readily. If the hole size is smaller than 4 or 5 grains across, you will tend to see clogging. And one way to sort of locate a clogging transition would be, say, to measure the average amount of mass that comes out between clogs. You start the flow, bang on it or shake it or whatever, start it flowing, measure the mass, and continue, until a clog forms. And then just do it, 10, 100 times, get the average mass discharge and plot that versus hole size. The bigger the hole, the more that comes out. And actually, if you look at this plot, it's a log linear plot, and the average mass grows quite dramatically with a rather modest increase in hole size. And it's easy to fit that to a diverging power law and locate a clogging transition. All right, so those are two iconic features. So let's go into these in a little more detail. Here's the discharge rate. It's a so-called Beverly equation.
I have a question.
Yes, Sriram, please.
You said, was it a log linear? I thought it was log, that picture.
Well, how about that? It's log. I stand corrected. Thank you, Sriram. And I thank Sriram again, because Sriram is the person who explained to me the Beverly equation when he was visiting me at UCLA in Andrea so long ago. So the Beverly equation is how fast what's the rate of mass discharge for a granular hopper or an hourglass? And basically you can get it by dimensional analysis. It's the mass density of the grains times the exit speed of the grains, which is given by the free fall speed for a grain going through a distance equal to the hole size, times the hole area. And intuitively, I didn't write this down. One reason why the exit speed is as such is because you can think about there being a sort of a transient arch that forms over the hole that maybe brings the grains to sort of momentary rest. So they're at rest, the arch is unstable, it's transient, it breaks, and then the grains accelerate from rest through a distance equal to the hole diameter, and that gives you the speed. All right, so even the idea of arches and clogging is sort of built into some of the intuition that's been put forth for the Beverly equation. But I'd like to emphasize particularly that the Beverly equation, although it shows a vanishing flux for a non-zero hole size, where the Beverly equation predicts or gives a 0 for the mass discharge rate is not the location of the clogging transition. You can see the Beverly equation works in this plot quite well, both above and below clogging. There's no hint in the mass discharge rate that there's a clogging transition. It's another way to say it. So there it is in this plot, the yellow region, right around 4.5 or so grain diameters. And there's no hint in the mass discharge rate that there's a clogging transition. All right, so how do we mark the clogging transition? And here's the first experiment I'd like to tell you about. It was done by an undergraduate, Hannah Sheldon, pictured here. And what she did is she took a hopper or a bucket of sand, and basically it was flowing, had a large hole, and then she tilted it. She just tilted it progressively. She increased this angle theta until the flow stopped. And she did that a few times to get a good measure of what we would call then the stop angle. All right. And then she did the reverse. She started with it clogged and highly tilted, and she untilted it until it started flowing. So thusly, she bracketed a line in what you might call a clogging phase diagram that separated regions of tilt angle and hole size. It would separate readily clogging regions from regions which always flow and never clog. So that's one way to map out the clogging transition that Hannah did. The other way, it harkens back to what I mentioned earlier about measuring the divergence of the average mass as you increase slowly the hole size. And here, Charles Thomas did so at different angles. So we could connect to Hannah's measurements, and you can see that the results are in pretty good agreement. So we're pretty happy about this as being sort of a clogging phase diagram that makes sense to think about. All right, so there's the clogging transition and some of its phenomenology. Now, I've got to tell you, we are a little bit uneasy still about this, because basically the average mass increases, and this plot is clearly log-log, so I won't make that mistake twice. Since the mass increases so dramatically and rapidly with hole size, you can actually fit it to two very contradictory forms. One where there is an actual divergence at a finite hole size, and one where it doesn't diverge until, well, the hole size is infinite. We've done about as well as anybody can do in terms of experiments. If you make the hole size infinitesimally, well, as we can control it experimentally in the lab, larger, suddenly you'd get tens or hundreds of kilograms coming out between clog events, which would take weeks or months to happen. So we're not going to be able to increase this at the upper end. At the lower end, we're already measuring average masses that correspond to just a couple grains coming out. So this is it. The data is not going to get any better, and the data is not good enough to distinguish two extremely contradictory forms. So on that basis, we're uneasy. We're further uneasy because there's no prediction for the value of either the critical hole size or the exponent. Side remark on point one, if you look in the literature, well, here I said the exponent's about 5, between 4 and 5. There are reports in the literature of exponents that vary between 2 and 12. Okay, so, and you can imagine why, because the dynamic range is probably not so good. But anyway, there's no theory for the values of either of these things. There's no signature of the transition approaching it from above. In the plot I'm showing here, where we're increasing the hole size, we're in the clogging regime and making the hole bigger and bigger. We're approaching the transition from below. I do not know. We've looked, we've tried lots of things. We can't find a way to locate the transition approaching it from above. So that gives us pause. And for me, the nail in the coffin is that we have an intuitive argument for this particular functional form, why the average mass might grow exponentially and hole size to a power. So let me take you through that argument next. Starting point is something I didn't tell you about, is that as part of doing the experiments, Charles measured not just the average mass that came out, he measured the distribution of masses between clogs. And the result is it's exponential. So clogging is actually in some sense a Poisson process. And if you take this and combine it with the Beverlew result I mentioned before, that the mass discharge rate is independent of time and filling height, you come up with the following intuitive picture. As discharge happens, you are sampling new microstates at a steady rate. So every click of time, there's a new configuration in the whole region and a new opportunity to form a clog. Well, let's suppose that there are two kinds of flow states, those that do and those that do not cause a clog to form. If you sample those at a steady rate, randomly, you get a Poisson process. You get an exponential distribution naturally. All right, so that intuitive picture is a starting point. All right, let's say it another way. So here on the right are snapshots at different times. So at tau 0, 2 tau 0, 3 tau 0, we have different flow states and different opportunities to clog, and it just goes. Maybe the nth time, here is a flow state that precedes a clog, and the next instance of time it does form a clog. Okay, so our interest is in the green versus yellow pictures, not in the red. The traditional way of studying clogging is to focus really on the zoo of arches and their stabilities, whereas I'm trying to switch points of view to focus about flow microstates and the two kinds. All right, so tau 0 in this, for me, that's a sampling time. It's how long it takes the microstate to change. It's how long you have to wait until you have a new opportunity to form a clog. And intuitively, this is set by the flow speed and the grain diameter. Basically, every time the grains in the whole region move down by 1 grain size, you have a new configuration and a new opportunity to clog. All right, so sampling time, sampling length, they're the same thing. All right, so I can write the average amount of mass that comes out as mass density times hole size times flow speed times the average duration of the flow. And so average tau is the average flow time for a clog. So average mass and average flow time, they're just proportionate, of course. The reason why I'm going to rewrite this is because then I can express the average. I can substitute in equation 1. In equation 1, you see the speed is the ratio of sampling length to sampling time. So the average mass is mass density times area times sampling length times the ratio of average duration divided by sampling time. Why do I do that? Because that, in effect, is n. That is the number of independent configurations I've sampled between clogging events. And reciprocal of that is the fraction of all the flow configurations that proceed, in other words, that cause a clog. So there we go, the average fraction, and this is going to be the thing that I'm most interested in, the fraction of flow microstates that cause clogs, the fraction of all the flowing states that are yellow rather than green, is given by the ratio of tau 0 to tau. And from equation 2, that's equal to things that I can measure macroscopically: the density, the whole area, the grain size, and the average mass. So there we go. There it is all together. Again, so this is one way. So we measure the average mass and we express it in terms of the fraction of flow configurations thanks to this little equation. And I like this very much as a way to interpret the data, because for me, it's kind of like making a macroscopic measurement of entropy. I've measured macroscopic things and I've inferred something about the microstates. And it also allows us to do a little calculation for what is average mass versus time. So let's do that next. All right. So remember, the phenomenology is that the average mass grows like one good fit is average mass goes like exponential in whole size cubed. That means the fraction of flow configurations goes down exponentially as exponential in whole size cubed. So that's what we're trying to understand. And we can do that with this expression here for the fraction of flow configurations in terms of average mass. All right, so first step in this little explanation is to think about how many grains are actually involved in forming a clog. Clearly, not all the grains in your whole hopper are important, only the grains in the whole region. So the ratio of whole size to grain size to some power stands to reason should tell us the number of grains that are actually doing the job. They're actually playing a role. So those are the number of grains involved. Now we're gonna make a wild assumption. We're gonna think about this not as a collective phenomenon, but just as sort of like an ideal gas picture, like the grains are sort of sampling their microstates individually rather than collectively. So let's say each grain has V1 single grain microstates that it can sample. Then V1 to the nth is the total number of microstates. It's the multiplicity of the system. But only some number Vs of those single grain microstates precede a clog. So therefore, the total number of system microstates that precedes a clog is Vs to the nth. And now we're done, because the fraction f that I desire is just the ratio of these two multiplicities. So an exponential raised to of whole size to a power just flies out of this argument very simply. And an interesting thing to me is the value of the exponent alpha. So remember, alpha here in equation 1 tells us how many grains are involved. And you might think that alpha should be dimensionality minus 1. If you think that only the grains that form the arch is important, right? How many grains are in an arch? That's the ratio of whole size to grain size to dimensionality minus 1. What we find instead is that alpha is actually dimensionality. And in fact, that holds not just in 2D, but also in 2 dimensions. You can do experiments in 2-dimensional hoppers. Other folks have done that before, and we've done it ourselves also, and that works also. So this exponential and whole size to dimensionality, I think is the proper way to think about and to describe the average mass as a function of whole size, and it's explained naturally in terms of the fraction of microstates that are involved in forming a clog. And that brings me to the end of part 1, where we do sort of the thermodynamics, if you will, of clogging. And we're gonna segue to the statistical mechanics, where we think about the actual microstates that are involved in the clog forming process. All right, and I should say, Sriram, thank you for asking a question. I very much welcome questions as we go along, and now maybe I could pause and see if there's anything about this first part that I could clarify.
Yeah, please unmute yourself and ask questions if you have, and then we'll move on.
Sometimes on Zoom, folks will put questions in the chat, but I can't monitor those.
I'm looking at them, and
Oh, thank you.
yeah, Sriram may have a question. I don't know.
Yeah, so I mean, I guess you can ask I can ask my first question. I was just curious about whether I should think of the thermodynamics and so forth you're talking about as really applying in the n going to infinity limit, or is it enough if your system is just a few times the whole size?
Let's see, it's kind of inevitable that the whole size be fairly small to measure these things. So in the end, we're really only thinking about a few grains, right? I mean, could be, I don't know, hundreds to thousands of grains are really probably the most, you're never in a thermodynamic limit of having essentially an infinite number of grains.
Right, but does something singular happen in that limit? I mean, when you think about the glass transition, for instance, naively you would think it's mostly about something fairly local, but now it's reasonably clear that there really is, that finite size actually changes the glass transition. So is there anything like that here? So supposing you did experiments keeping everything except the overall height of the box.
Yes.
Same whole size, go to bigger and bigger sizes. Is there something singular in that limit?
That's a great question. So I brushed that under the rug in my discussion. So as part of measuring clogging statistics, we did experiments systematically varying the average fill height as well as the average diameter of our container, and we found no signal. Now, we didn't look very hard for making it small. I'm pretty sure something will happen if we were to make the diameter of our container pretty small compared to the hole size, but we haven't looked for that. And I'm not aware of anybody that has, but that would be an interesting thing to consider to follow up your question.
Right, okay, thanks.
I have a question.
Yeah, go ahead.
Or a Simco. Does your model eventually approach the state of a liquid, a very viscous liquid, because it would also be coming down as drops?
Oh, yeah, I don't know. I tend to think not. I tend to think of a liquid with, say a bucket of water with a small hole size coming out of drops as being dominated by surface tension. And I don't think of there being a surface tension in a granular system. So I tend to think not. But it is interesting to compare and contrast those cases.
I was thinking more something like honey or wax, something that's very viscous, but still would be coming out in drops.
To me, changing the viscosity for fluid in a bucket is just changing the time scale for the phenomenon.
Okay.
It would just slow things down, unless you made it sort of so the material was glassy. And now
Thank you. Thank you.
Okay. Great. Yeah, great question, Oris. Thanks.
Okay, thank you.
If there are no further questions, maybe we should move on.
Yeah, good. So let's think about the microstates. And here's our first foray. We're going to try to reduce the scope of the playing field a little bit here. What we're going to do first off is we're going to think about how behavior changes if we were to do it all underwater. So here is a hopper in a fish tank. Okay, no fish, but importantly, no air either. So there's no capillary effects, there's no surface tension effects. It's just doing it all underwater. And if you look at it, the grains are still closely packed. The packings of the grains are really not any different in air and underwater. Okay, so the grain position microstates may not be changed, but for sure the momentum microstates are. You've gone from a system where the grains are sort of jittering around and collisional in the region of the hole size to being viscous and overdamped. So the momentum microstates we've changed significantly, maybe without affecting the position microstates at all. So that's the philosophy here. And when we do this, the Beverly equation or something like a Beverly equation holds. So now the flow speed is not set by free fall, but really the terminal fall speed of a grain. And this is work done by undergraduates, I'm happy to say, in my laboratory. So here's Taya Wilson, Charlotte Pfeiffer, and Nico Messenger. Actually, Nico's a high school student, contributed to this. So there is something like a Beverly equation and a Beverly cutoff that's a little bit larger underwater than in air. Okay, so Beverly holds. Clogging phenomenology also holds. Okay, so on the left is the I should have spelled out that basically it's the cumulative distribution function for the average amount that comes out, and it decays exponentially. So the distribution is exponential. It's Poissonian also. Furthermore, on the right plot, here's the average mass versus hole size cubed. And now it is a log linear plot because we plotted versus whole size cubed. And you can see we get nice straight lines. And that means that, that you can get a good description of this as being, average mass is exponential whole size cubed. So that phenomenology is unchanged. And furthermore, the two data sets we're showing in orange and aqua are almost indistinguishable. Those correspond to the same grains and the same hole sizes, just in air versus underwater. So changing the interstitial fluid from air or maybe vacuum essentially to water didn't change this at all. Basically, the same number of grains come out before you form a clog. Of course, it takes a lot longer because the discharge rate's slower, but basically the same number of grains come out before you form a clog, which is kind of cool to think about. If you take this and plot it as the fraction submerged, it's a little bit easier to interpret, to me anyway. And you can see that here it's a little bit larger. F is a little bit larger if you're underwater. So you're a little bit more susceptible to forming a clog if you're underwater. But basically, you're not much more susceptible. To the extent that these are identical, I would say is lends credence to the idea that the momentum microstates are not important. If momenta were very important, then these should be vastly different. They're not so different, so momentum basically doesn't play much of a role. Basically, it's the position microstates that are key. They're the key microscopic degrees of freedom for the clog formation process. So that's the idea. All right, that allows us then to go to town measuring position microstates. And we can do that in 2 dimensions pretty easily. So here's a 2-dimensional hopper. And Jesse Hanlon is a graduate student who's doing this. And we're working on analyzing it with Andrea, who is on the line. All right, and our question is to distinguish the flowing states from the clog forming microstates. And the picture here, if you read it from left to right, if you look at just one row going left to right, you're looking at successive microstates. Okay, so 1, 2, 3, 4 flow states. So click, 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 click. Then there's a clog forming flow state, and then finally it's clogged. And I don't know about you, but when I look at this, I can't see a difference between the flowing states and the clog forming states. I can't tell if it's going to keep flowing or if it's actually going to end up being clogged. I just can't tell. But, and the reason why is because, well, it's a multi-dimensional process. There's lots of grains involved, not just the ones that form the arch, but in a region above the hole right? Some large number of grains. It's not just the arch forming grains that are important, it's the ones above it too. That's what's implied by the previous experiments, remember. So whenever anything is so multidimensional, you can turn to machine learning tools, artificial intelligence, to help identify the differences between the flowing states and the flow that leads to more flow and the flow that leads to clogging states. And the way we'll do that is take advantage of methods that Andrea pioneered. And the idea is to just measure different aspects of the structure. So measure structure functions, okay? Measure lots of them, okay? And in principle, you could measure momentum. You could concoct microstates that describe all the momenta, the rotation degrees of freedom, contact forces, and things like that. But we're going to focus, just first time out of the box, on position microstates, and also in particular on just the simplest ones that you can concoct, namely these functions G, which basically count the number of grains that are in rings of radius mu and width sigma, okay, centered around the outlet, okay? So this is a family of structure functions that describe what's going on in the whole region as you vary mu and as you vary the ring width sigma. So those are all the structure functions. You can measure tons of those. And for us, we measured on the order of 100, a couple hundred, and then did the following. Basically, here's if you have 100 structure functions, you basically have 100-dimension structure space. And you're trying to find a hyperplane in that structure space that separates the two different kinds, the two different classes of microstate. We're trying to do a classification problem here. So here are two of those dimensions. It could be that structure functions 1 and 2, most of the clog forming flow microstates are in the upper right, and most of the continued to flow microstates are on the lower left. And you can just draw by eye pretty easily what is the hyperplane that separates those. So the idea of a support vector machine, which is one of the simpler kinds of ways of doing machine learning, is to find that hyperplane is just doing some linear algebra, in fact. So we do that. And then we also take advantage of a trick that Andrew developed, which is to measure the distance of the system of a particular flow state from that hyperplane. That gives you a measure of how susceptible the system is to forming a clog. The farther you are from the hyperplane to the right, the more susceptible you are to clogging, and the farther you are away from the hyperplane in the lower left, the less susceptible you are to clogging. So this quantity C, which is signed, we'll call clogginess, and Andrew developed with her group a measure of softness, which did the same thing for describing the susceptibility of particles to rearranging in glassy near jamming systems. So we're doing the same thing here for the two clogging states, and instead of calling it softness, we'll call it clogginess, because that's an ugly word, and I can't think of a better one. So there's clogginess. And it basically works, okay? So here are some results. So on the left is a plot from one of Andrea's papers showing the distributions of the probability of finding a given softness value for basically everything versus those that cause rearrangements. And those two things are separated. And the same things happens here. Okay, so the two distributions are pretty well separated. And with this, we can actually successfully then classify basically almost 90% of the flow microstates that lead to clog formation. So we're pretty excited about that. One of the cool things that comes out of this kind of analysis is that you can then go back and ask, well, which structure functions are important for this process? And To find that out, you do something that the computer scientists call recursive feature elimination. Basically, you throw away the structure function that has the least weight and retrain, and just keep doing that until your accuracy starts to decrease. And that way you can get a measure for, you can basically rank all the structure functions in order of importance. And here in Jesse's first try are the 4 that were important. Basically four different ones that are basically, you know, a few grain diameters, and with widths they're comparable to the particle size. Okay, so basically counting particles in a series of these rings will give you a good idea of whether or not the system is going to form a clog. All right, and with that, let me wrap things up, tell you my conclusions. So the classic way of thinking about clogging is to consider the zoo of arches and their stability. So confronted with a static packing that is clogged, you ask, how stable is it? How hard do you have to bang on it to unclog it? And so forth. We're taking a very different point of view. We're focusing on the flow microstates that lead to clogging. And that naturally gives us a very natural and very easy way to think about and explain why the average mass grows exponentially in whole size to a power. And it opens up a new field of investigation where we can try to classify flow states using machine learning methods. And where we're at in that is we have some initial success, but we're looking for better statistics. Okay, we could perhaps do better training if we had more data. Okay, so we need more data. We'd like to do this in 3D, and eventually the goal is perhaps you could take evasive action, right? If you are monitoring in a smart way the discharge of grains at a slow rate from a hole that's not too large, and if you see that it's about to form a clog, you could do something to prevent, you could act on the flow state and prevent a clog from forming. And that could be preferable from waiting it to clog in your big industrial hopper than coming with a sledgehammer and beating on it to get it to unclog. So this could actually also be useful. I hope, maybe, who knows? Okay, so let me thank the folks involved. So our clogging story started with Hannah Sheldon, an undergraduate, continued with Charles Thomas, PhD student, then Juha Koivisto, a postdoc, and is currently now in progress with Jesse Hanlon and with Andrea. And the other folks that were involved, not in clogging per se, but in discharge underwater, are a series of undergraduates, Taya Wilson, Charlotte Pfeiffer, and Nico Messinger. And with that, let me stop. And thank you for your attention, and invite more questions.
Thank you. And let's give Doug a round of applause. Just unmute yourself and let's do a real one. This is fantastic. Thank you so much. Yeah, open for questions, please.
Doug, I have a just very nice talk, and I'm not from your place there, so I just want to say thank you for the opportunity. Just a question, but before your conclusion slide, you have this essentially the first, instead of looking at the arc, rather you have going for, let's say, the first, like the next 3 layers basically, as a way to let's call it the important descriptors for your machine learning. But isn't that basically means, as far as evasive action, it will be very difficult to predict then, right? Because you have to be monitoring at the very vicinity of that area for you to be able to have an effective evasive action. I'd like to see what your comment about that.
Oh, that's a good question. And I don't know how to answer that. It's nothing that we've explored, really. But I would say that maybe we can prevent clogging. We may not have to act on all those interesting, important grains. It may be enough just to act on the grains in the first lowest row. basically, if you remove the keystone, the arch will crumble. So it may be pretty easy to prevent clogging from forming if you're in a flow state. That would be my hope.
I have a question.
Yeah, Chris,
happy-
go ahead.
Well, yeah, again, really nice talk. I really enjoyed listening to it. Nice physics. With your submerged experiments, have you accounted for and have you taken advantage of buoyancy? If you make these things really buoyant, you're essentially changing the acceleration of gravity, which could be pretty neat.
Yeah, that's a good question. So I would say we changed the densities. The only way we've done that is by changing the densities of the grains. In fact, Nico, his job was to do this with lead pellets. So we did change the densities in there. And that's how we were able to map out that the terminal flow speed is important. So I'm not sure, I mean, effectively the effective gravity, the effective downward pulling force is a combination of just mg down and buoyancy force up. So that is built in to the terminal falling speed. So that is kind of built in.
Well, but you could get to the point where you're neutrally buoyant. I think just the idea that you have a readily variable G, right? You can go from 9.8 to 0. You can do microgravity experiments. You can get money from NASA. You can go to Mars and do these experiments. You got all kinds of opportunities, right?
Yep. So yeah, that's a good point. And actually, I could say something along those lines. So people have gone in the other direction. There's a group in Europe, and I'm very sorry, I'm blanking on the name of the PI. Maybe it'll come to me.
Diego Maza?
No, Northern Europe,
Oh,
in Sweden.
okay.
And he did it in hyper-G.
Yeah.
Okay, so the European Space Agency has a facility for basically taking something and rotating at very, very high speeds over, meters. So he could look at hyper-G. There are people that have looked at discharge of bubbles to go upwards. Okay, and there's a kind of a Beverly-like equation for those. And I myself helped, and actually with the help of Ted Brzezinski, who is pictured here in the lower to my right in the photograph. That's Ted Brzezinski. He's now an assistant professor at Haverford College. And Ted and I together helped direct a team of undergraduates do some microgravity experiments on the KC-135 Vomit Comet that does these parabolic flights that goes up and down. So basically, to look at discharge it wasn't 0G, it was low G to do that. And they had a lot of fun doing that. We didn't learn anything, okay? The data didn't come out so well.
Well,
but they had a lot of fun.
Neutral buoyancy in a stationary lab is better than puking on a comet. So
there you go.
Can I ask another question too? And it's related to the Orostinko question with regard to liquids. When I look at flour, it doesn't flow the way grains of sand do. And I think what you've got is a hard sphere limit with no attractive potentials. But once you start getting a little bit of attractive potential, which you can start getting with really tiny grains, the physics is going to change. Have you gone into that realm?
I totally agree. Totally agree. You're exactly right. So we are in the hard sphere limit that the grains are essentially rocks and they interact just by friction and contact forces. There's no cohesion between them. Small grains, if you make them smaller, then exactly as you said, they'll become cohesive. Van der Waals forces play a role, charging effects play a role. They become cohesive, and that's pretty unavoidable. So flour acts in a very different way from the kinds of systems we've looked at. And for that, they clog more. Actually, they can, you can form, well, just looking at the surface, the angle of repose becomes not so well defined. Just the surface of the system isn't so flat. You can develop overhangs and things, and you can just see cohesive. And when it's cohesive, oh boy, does it clog. It's hard to get it to flow out a hole. Basically, you have to pour it from the surface. Or in a sifter, a flour sifter, the only way you can sift it through a screen is by scraping it with a wire. So yeah, clogging for cohesive grains is a totally different story. And I should say we haven't done anything in this regard.
Yeah, but of course, the limit eventually gets to be liquids. And so just all kinds of phenomena along the way. So this is really exciting. I really enjoyed listening to you. Thank you.
Thank you. Good questions. Thank you.
I have another question. Thank you for your talk, by the way. And
Yeah,
my question is, have you considered shaking your system with ultrasound?
No, I personally have not done that. I think that's a good question. And it would tie into a potential way of doing evasive action. So if we had some kind of shaker mounted to the side of our sample and we saw it was about to clog, we could shake it and it would unclog. So, and you could also fluidize the system to various degrees by shaking it at different rates. Could be ultrasound, could be different frequencies. You can shake it and fluidize it, and that'll affect the clogging behavior for sure. Absolutely for sure. So I think this is another fascinating direction that this could go in. We haven't explored that direction.
Just one thought. Xiaoping Jia is on the line. I don't know if Xiaoping wants to comment on that because he's an ultrasonics person.
Xiaoping has done lots of work, lots of interesting work, fascinating
Yeah.
work, excellent work on sound in sand.
Yes, thank you. It's a very nice talk. Yes, yes, the ultrasound compares to the low frequency shaking, for example, could modify the interparticle friction. So in the zoom of the clogging, it could provide some useful information. So it's a very nice talk. We would like probably to have some try on that direction. Yeah, it will modify the interparticle friction force. So this is the idea.
Yeah, I had a question about that, but I think that's gotten answered. So I'll let Alex ask a question. Alex Vakakis from Urbana is here, so he wants to ask a question.
Yes, hi. I enjoyed very much your talk. Thank you.
Thank you.
I have two questions. The first question has to do with your statement that you made earlier in the beginning, actually, of your talk, that the boundaries play an important role in clogging and jamming, right? So I assume that the boundaries that you're using are rigid boundaries, right? So my first question is the flexibility of the boundaries and also of the exits affecting jamming and clogging? That's my first question. And my second question is, how important is the friction between granules on this phenomena? If you could comment on that. Thank you.
All right, thank you. So the first question about the boundaries, I don't know about the role of flexibility and the compliance of the material that you make the wall from. We haven't varied that. What we have varied in the past occasionally is the roughness of the boundary. It's not really the same question, but it is something, the boundary can affect behavior, and making it rough on the bottom does affect the clogging statistics. So if it's smooth on the bottom, it tends to clog not as readily as if it's rough.
Roughness is related to friction, I guess, between the granules and the boundaries, right?
Yeah, I think that could be a good way to think about it.
Right, but flexibility, what I have in mind is something a little bit different, which is, instead of the boundary being completely rigid, what if the boundary is able to be flexible? Basically, in relation, I guess, to the flexibility of the granules. So I wonder if that would be of interest as a research topic in the future.
Yeah, I think that's an interesting idea that hasn't been explored. So I guess the idea would be to make it comparably soft as the grains, or maybe make the grains rather soft also. So like the bubble experiments. So you could have a soft interface somehow, something soft rubber, comparable, that's easily deformed by a bubble. And you could see, I would expect there should be different behavior.
We have been working on ordered granular media. I'm in mechanical science engineering department, so I'm more interested in applications related to shock, vibration isolation, and on the acoustics of ordered granular media. So, and we are able to study the interaction of ordered granular media with flexible boundaries. So I was thinking that this might be an interesting topic that I could look at in the future with granular flows.
Uh-huh. Yep.
Alex, your question made me think about, you have a system that you can probably squeeze, because if the walls are soft, then just like squeezing toothpaste out of a toothpaste tube, and what effect that would have on unjamming or breaking down the clogging process here.
Or you might be able to oscillate it, Shurajit.
Yeah, exactly. Yeah,
So you use a characteristic frequency there. So I wonder how that would affect the.
Yeah, the physics would be different if you squeeze it hard once versus do it like that. Yeah, that's a fascinating problem, actually.
I was going to say, to answer your second question about friction.
Yes, please.
So we changed the granular materials a little bit in the course of our experiments, but we didn't specifically change the friction coefficient directly. So, for example, by taking glass beads and making them progressively rougher. People have done that, but we haven't explored that direction. I can say that where people have changed the effective friction coefficient more dramatically is by looking at clogging with the bubbles. So those are much more slippery, right? There perhaps is very little or maybe no sliding friction between bubbles. And there, the cutoff in the Beverly equation and the critical hole size for the putative clogging transition are much smaller. So I think the more frictional you make it, basically the easier it is to stabilize arches.
Great, thank you so much. I enjoyed your talk.
Thank you.
Can I have a question?
Yeah, go ahead, please.
Okay, so again, just a note that Perseverance right now is actually sampling, collecting samples in March. So let's hope that actually you are being consulted on this. Otherwise, they need to know how to shake it. What is the effect, for example, of going back to the microstates? Let's suppose if I change the aspect ratio of your particles, how that actually would change the analysis on the microstate?
Oh, that's a fascinating question. I think that our structure functions may no longer suffice. I think you may have to keep track of the orientation of the grains. That could well be important. We haven't explored that yet, but I will say that Charles Thomas did do experiments on looking at the Beverly equation and the flow above and below the clogging transition for things like elongated grains like rice and squashed grains like lentils. So the Beverly equation works really well for both of those cases. Okay, and there's a cutoff, and it changes systematically with the nature of the grains and the aspect ratio of the grains, whether it's prolate or oblate. That definitely plays a role. And I think furthermore, it's going to actually break down if you make the grains so elongated that they're like rods, they're like pins, needles. Couple groups have looked at that limit in particular. So, so Scott, the Rochester Institute of Technology, Scott Franklin has looked at that. And the group in Germany, Ralph Stenarius and Thomas, I don't know how to say his last name, starts with the B, have looked at this also. And there they've actually done it in 3 dimensions using macroscopic wooden dowels and X-ray imaging.
Thank you. I enjoyed the talk very much. And Rice, give me an idea to do home experiment now.
Awesome.
Yeah, right. Kitchen experiment. Yeah, I actually had exactly the same question that Ridwan had. What if you were to sort of mix rice and sesame seeds? How would that work out? Because that gives you 2 very different types, and actually, I suspect it might flow well.
Yeah, so mixtures and polydispersity, all these things.
Yeah, I had a student that ran kitchen experiments for a couple of years on this problem, and we did use, oil and stuff like that to change friction, and the behavior changes that we saw weren't as dramatic as we had expected, although we pushed the limits quite a bit. So the stuff you said kind of fits in very nicely with that. We never wrote it up. It was an undergraduate project. Never wrote it up because couldn't explain. Now that Andrea has this nice theory, might be worth going back to the problem. And thanks, Andrea, for joining online.
Oh, yeah. Thank you.
This is very cool.
It would be interesting to discuss what you were talking about just now.
Oh, yeah, I'd love to. I'll have to dig it up. It was a few years ago. The student moved over to astronomy, but yeah, a whole bunch of experiments, and we got some deviations from Beverly's law, but it was all done in the kitchen. I don't have a lab being a theoretician, as you can imagine. So.
Yeah, that sounds interesting.
All right, any further questions? If not, let's thank Doug for a fantastic talk, and thank you so much for joining and making it into such a fun session. Every other Saturday or so we do it. I've tried to put all of you on my mailing list, and I'll try to keep it going as long as possible. It started with COVID and last June, and it's been quite a nice set of talks we've been having. Thank you very much. Thanks, Doug. Thanks, Andrew.
Thank you.
Thank you.
Thank you. Bye-bye now.
Thank you. Bye-bye.
And I'll post the stuff on the YouTube channel. And next week, not next week, in 2 weeks, we have Roland Geyer from Santa Barbara talking about plastic pollution, which is a somewhat different kind of physical problem. But we'll get there too. Bye-bye.
Thanks. Bye.
Bye.